Differentiation of parametric functions. So we start off with two parametric equations. So x and y are both given in terms of the parameter t. We differentiate each, dx by dt, dy by dt. The gradient of the curve will be the change in y over the change in x. So we need dy by dx. So we have these two derivatives and dy by dx, which we connect together using the chain rule, like this. One thing to be careful with is that's dy by dt, exactly the same as this. However, this is not dx by dt. You have to take dx by dt from here and flip this over and then put that here. Example 1, we have x and y given in terms of a parameter t. We differentiate each one, so dx by dt, 2t, dy by dt, 3t squared. Our curve will have a gradient which is the change in y over the change in x, so we need dy by dx, which is given by our chain rule. Now we need to flip over the dx by dt to get dt by dx, which is 1 over 2t, so this will replace this, and the 3t squared goes here, like so, and then we simplify. So to work out the gradient of any point on the curve, we first need to know the value of the parameter t at that point, and then you substitute the parameter into here, multiply by 3 over 2, and you have the gradient. Example 2, we have some parametric equations, and the parameter t takes a value between -4 and 4. So I'm going to sketch the graph first. So let's make a table of x and y values along with their parameter t. So t equals -4 there, t equals +4 in that interval, and all of these x values come from x equals t minus 2, so take the value of t minus 2, and for the y values take the value of t, square it and add 1. For example, -2, square that, we get 4, add 1, we get 5. And now we have coordinates in pairs like this, and then we can plot these on a graph and we get this. And we can see as t increases, we can imagine a particle moving along this path on the graph until it reaches here when t equals 4. We don't go any further in this direction or this direction because we were given the interval for t. T is between -4 and +4. No value of t outside this interval. So let's see if we can work out the gradient of the graph right here when t equals 4. And we'll do this using parametric differentiation first, and then we'll change the parametric equations to Cartesian equations, and we'll have a go at differentiating again and working out the gradient, which should be exactly the same. So chain rule, dx by dt is 1, so if we differentiate this, and dy by dt, if we differentiate this, is 2t. We put them into the chain rule, and be careful with this one, it's not dx by dt, it's dt by dx. So you flip this over and it will give you 1. So dy by dx, when simplified, is just 2t. So to work out the gradient anywhere, we need to know the value of the parameter t. So when t is equal to 4, the gradient on the graph is 8. Okay, now we're going to try the same thing in Cartesian form. So we need to eliminate the parameter t. So I'm going to rearrange this equation to make t the subject, like so, and then I'm going to substitute this t, x plus 2, into here. So then we get y is equal to x plus 2 squared, because it was t squared, this is t, We need to square it, then add 1. So now we have an equation with just x and y. This is the Cartesian form. We have eliminated the parameter t. And then expand the brackets and simplify. So let's work out the gradient again for x equals 2. And on the graph it's the same point. When t was equal to 4, x was equal to 2. So if we differentiate, so dy by dx is 2x plus 4, then substitute x equals 2 into here, and we get the same value as before. The gradient's 8. Example 3, we're looking for dy by dx, so we differentiate both of these parametric equations. Then we use the chain rule. Again, that's dx by dt, and if you flip this over, you get 1 over 3t squared plus 1. Simplifying, the gradient when t equals 2 is 4 over 13. Now what will the gradient be for this point on the graph? So x is 30 and y is 10. Okay, so we use the equation for x, make it equal to 30. The equation for y, make that equal to 10. If we solve these, so this one here, it gives two possible values of t. So when t equals minus 3, the y coordinate is 10. When t equals 3, the y coordinate is 10. So which of these values is valid? So if we substitute in minus 3 and then plus 3 into the equation here, the one that balances this equation is the correct value of t that we're looking for. So I'll put in minus 3 first into here, and I'll get x equals minus 30, not 30, which is what I'm expecting. So it's not minus 3. If we try x equals 3, that one works. So I know the value of the parameter t is equal to 3. So the gradient, if I substitute t equals 3 into the derivative dy by dx, I'll get 3 over 14. So if we want to work out the equation of the tangent at this point on the curve, so the tangent is just a straight line, so if we use the y minus y1 equals m times x minus x1 format, we end up with something like this. There's the gradient of the curve, which is the same as the gradient of the tangent. If it was for the equation of the normal, we have to modify the gradient here. We have to flip it over and change the sign. We'd get this. Example 4, we have some parametric equations. Differentiate, chain rule, dy by dx, and then simplify. For practice, try these questions.